In the first video on section 5.4, we were dealing with the theory behind triple integrals and how to rewrite them as iterated integrals. First as a single integral inside of a double integral, and then as a series of 3 iterated integrals. In that video, we discussed how to do it and how to change from one orientation to another, looking at them as types 1, 2, and 3. We also looked at how we can calculate the volume of the domain region by setting the integrand to be 1, and then use that information to help find the average value of the function of 3 independent variables over that domain. In this video, we simply want to work more examples of how to change from one orientation to another, how to change the order of integration. This is simply a working practice on how to do this. Let me share my screen so we can get started. We're going to start with example 6, which is actually a reworking of example 4 from the first part video. In this case, we want to rework example 4, treating the domain as a type 1 integral. And that's where we cast the projection into the xy plane. Our function of 3 independent variables is f of xyz equal to yz. And E is the region bounded by a paraboloid x equal 2y squared plus 2z squared minus 5, and the plane x equal 1. Let's take a look at calcplot 3D so we can remember what our region in the domain looks like. Again, this is a function of 3 independent variables. What we're looking at here is the domain region, which is the solid consisting of this paraboloid cut off by the plane where x equal 1. Now, what we want to do is we want to cast the projection this time into the xy plane and work it as a type 1. Remember that when you're casting the shadow into a particular plane, the variable that's not a part of that plane is the one down which you shine the flashlight to cast the shadow. And you need to take the widest part of this solid in order to cast the shadow. Oftentimes, this would be where 2 surfaces intersect. In this case, we do have an intersection between the paraboloid and the plane where x equal 1. That casts the widest part of our particular solid. To project into the xy plane in calcplot 3D, we want to hold down the Alt key and hit the Z key. This will put it into the xy plane, and I can move it down a little bit so that you can see it a little bit better. Maybe it's not working quite right. It's not wanting to shift. So when we're looking at this, this is, in a sense, the shadow that is cast into the xy plane by this paraboloid cut off by a plane. So when we're looking at it, we're going to see that we have a right opening parabola in the xy plane. Now we can write x as a function of y or y as a function of x, whichever one you want to go with. If you choose y as a function of x, then you're going to have a square root, and you're going to have an upper arm and a lower arm, where the upper arm corresponds to the positive square root and the lower arm corresponds to the negative square root. If instead you want to write x as a function of y, then it's possible that you will not, in fact, need to have the square roots. Instead, if you write x as a function of y, then you're moving from, on the narrow end, on the left side of the x-axis, from the parabola up to the plane where x equal 1. Let's go ahead and take a look at the algebra required to do this. If we're looking in the xy plane, then the value of z is 0. In this case, this gives us the equation x equals 2y squared minus 5. And again, this is simply taking our paraboloid equation and replacing the z term, the z variable, with 0. Now, we can write this, if we're looking at this, we're shining a light down the z-axis. So what we're getting is, of course, an equation in terms of z. So if we're going to solve for the inner integral first, we have to integrate with respect to z first. Now, when we're integrating with respect to z, we have all three independent variables involved. This picture applies to the double integral, which is the outer set of two integrals. This does not apply to the inner integral, which is going to be with respect to z, the one we're shining the flashlight down. In that case, we start over again with the paraboloid equation, and we have z equals plus or minus the square root of 1/2 the quantity x minus 2y squared plus 5. This is going to give us our upper and lower. When we're looking at this, however, remember that we're going to integrate with respect to z from this lower value to this upper value. Then, after we're done with that, we need that two-dimensional projection into the xy plane. That two-dimensional projection is characterized by x equals 2y squared minus 5. So x goes between 2y squared minus 5, the paraboloid on the low end of x, to positive 1 as the highest value. And the best way to see this, of course, would be to rotate the previous picture that we had above here and put the x-axis going up and the y-axis going across. And if you do that, then you'll see that it does indeed go from the paraboloid up to the plane. So what I've done is I've simply flipped the image of our projection into the xy plane so that this is now the y-axis and the x-axis is coming up. So I'm writing x as a function of y because then I won't have to take the square roots again. So when I'm looking at this one, notice that on the bottom, with respect to x being the vertical axis now, then I do have the paraboloid on the bottom and I have x equal 1 on the top. And when I do that, that is going to change my limits of integration. And that's going to set my limits of integration with respect to x to go from the parabola 2y squared minus 5 up to the plane x equal 1. Then after that, we need to find out what the value of y is. If we again think about what we're doing when we're doing this, we need to find the widest part, and we're looking at the projection, so we need to know what the value of y is on this particular projection. What is the lowest value of y used? What is the highest value of y used? And you can see that the lowest and highest y value are not where it intersects the y-axis, but actually where it intersects that plane. And it intersects the plane at the circle, y squared plus z squared equal to 3, which tells us that y is going to go between negative square root of 3 and square root of 3. The other way that you can get that, of course, is by setting the two equal, moving the negative 5 to the other side so that you get 2y squared equals 6 or y squared equals 3. And then you have that y is plus or minus the square root of 3. Let's go ahead and pause the video while we work out the integration, and then turn the video back on and we can look at the answer. So now you can see what this triple integral would look like if you were going to project into the xy plane first, meaning you have to integrate with respect to z first. Because of the radicals, and it looks like I've got a typo here, this should be between the negative root and the positive root, so I'll fix that. When we're looking at this, this is going to be more difficult to evaluate. Now, we've already done this one twice before. The previous time we looked at example 5 when we worked it, of course, as a, well, didn't quite go up there, as a type 3. And when we worked it as a type 3, we found that even when we were going with respect to y first, it looks like I've got a typo there too. Oh no, that's on a different part. It looks like, again, that we have some difficulty here in our limits of integration because of the radical. However, when we did it instead as a type 2, which was the original, casting the shadow as a type 2 into the YZ plane, we found that we got a more simplified integral, which gives us the integral that you see here. And after we were able to evaluate this one, notice that the interior integral, the single integral, is a much more reasonable limits of integration. However, the double integral got a little bit more complicated because we had to use polar coordinates. So what you want to do is evaluate which one would be easiest first and which one might cause problems later on. This is really a judgment call as to what's the best approach to solving that particular integral. We now want to go ahead and turn our attention to example 7. In example 7, we have a different solid. We have a new function of 3 independent variables, f, which is equal to y. The fact that it only has one variable does not make it any less a function of 3 independent variables. We are calculating in 4-dimensional space on a 3-dimensional domain. Our domain is the solid in 3-dimensional space E, bounded by y squared plus z squared equals 9, which is a circular cylinder, the plane y equals 0, the plane x equals 0, and the plane x equals 5. So you can see on the image on the left that we have this, well, tube, if you will, a circular tube, and we have 2 planes that are parallel, x equals 0 and x equals 5. And then we have a plane that's perpendicular to those, that's y equal to 0. So what region are we cutting off here? When we cut this one off, what we're really getting is half of the cylinder cut off on either end. So we have semicircular ends and sort of a, well, I guess you'd call it a hump in between, all right? So which projection do you think makes the most sense to use? Let's look at this one now on CalcPlot 3D. And again, here is the general shape, and you're cutting it with these 3 planes through that cylinder. When we cut it, we end up with this shape that you see here, and you can see the semicircular ends of the shape. So what we're trying to evaluate in this particular problem is, which way do we think we might want to project? So we have options here. One thing you might want to do is go ahead and project into all 3 planes and see which one looks like it might be the easiest to calculate. One option on this one is to shine the flashlight down the x-axis because the cylinder is symmetric about the x-axis. That would cast the shadow into the YZ plane. Let's take a look at what that would look like by hitting Alt-X. Now, as we're looking at this, I can't get all of the plane off, but basically we have a semicircle coming around like this. So we have a semicircular end. So our shape is really the semicircle. When we're looking at that, how would we be able to calculate? Now, the easiest regions to compute over are rectangles, followed by circles and semicircles. So this is a reasonable projection to do. When we look at this again from the view of the projection cast into the YZ plane, we do get a semicircle of radius 3. Because it's being cast into the YZ plane, we know the value of x there is 0, and the intersection with the 2 planes, x equals 0 and what was the other, x equals 3 or 5, I can't remember, is not going to change the shape of the end cap. It's still going to be a semicircle of radius 3. Setting the x to 0, we get y squared plus z squared equals 3, which just tells us it's a circle of radius 3. So we're dealing with half of that circle. And if we're projecting into the YZ plane, the y becomes the horizontal axis and the z becomes the vertical. And because we want the right half, we could write that as y equal the positive square root of 9 minus z squared. The left half would be negative the square root of 9 minus z squared. If we wanted an upper half, that would be z equals the positive square root of 9 minus y squared. and the bottom half would be z equals negative square root of 9 minus y squared. However, we want the right half, so we want to solve for the independent variable y in terms of the dependent variable z. In this case, our z value is going to go from -3 to 3, but our y is going from, on the left, y equals 0, which is, of course, this plane here, over to the semicircle, y equals the square root of 9 minus z squared. Now we rotate it again so that we can determine the limits of integration with respect to the inside integral, the single integral. So we've already computed what the outside ones would be. Let's go ahead and write those down now. Z goes between -3 and 3, and y goes between y equals 0 and y equal the positive square root of 9 minus z squared. That's our double integral part. Now our single integral, which is going to be on the inside of that, is going to have to be with respect to x. So to determine what it's going to be with respect to x, we rotate the image so that the x-axis is pointing straight up and so that we can see the YZ plane on the bottom. When we do that, we look to see in this solid region, which looks like half of a semicircular tube. When we're looking at this semicircular tube, then the bottom surface is given by x equals 0, that plane, and the top surface is given by x equals 5, the upper plane. So this is going to give us our limits of integration, that x is varying from the plane surface on the bottom to the plane surface on the top. And our integrand was y. So we have the integral from 0 to 5 of y dx first, followed by the integral from y equals 0 to the square root of 9 minus z squared with respect to y second, followed by the integral from z equal -3 to 3 last. Go ahead and pause the video to work this one out, then turn the video back on so we can compare our results. So in this case, we want to go ahead and integrate with respect to x first. So the integral of y, being a constant as far as x is concerned, just becomes xy. Evaluating from x equals 0 to 5 gives us 5y for the new integrand. Then we integrate with respect to y. Remember that y is going from 0 over to the semicircle on the right. So this gives us from 0 to the square root of 9 minus z squared, writing y as a function of z. In this case, then, when we integrate, we get 5/2 y squared. And when we evaluate, we get a new integrand of 5/2 times the quantity 9 minus z squared. This becomes the integrand for the outer integral with respect to z from -3 to 3. When we integrate, we get 45/2z minus 5/6z cubed. Substituting in the limits of integration and simplifying gives us an end result of 90. Now, is there another way that we could have set this up while still treating it as a type 2, where the projection is into the YZ plane? And the answer is yes. I have this set up here as first with respect to x, then y, then z. To treat it still as a type 2, I still need to go with respect to x first, but I could change the order of integration of the outer two. In order to do that, I have to write z as a function of y. So if we return to the projection into the YZ plane, remember that the equation of the semicircle, it's not x, it's y squared plus z squared equals 9. Then if I want to write z as a function of y, I isolate the z and I get plus or minus the square root of 9 minus y squared. Now, in this case, we want to integrate from the bottom, which is the negative root, to the top, which is the positive root. And then our y goes from 0 to 3. So in this case, we could change the order of integration by rewriting it as z a function of y. And that would give us the integral you see down here in blue. We would have on the inside the integral again of y from x equals 0 to 5 with respect to x. Then our second integral, we would switch the order of integration from dy dz to dz dy. Z would go from negative the square root of 9 minus y squared to positive square root of 9 minus y squared. On the outside integral, y goes from 0 to 3. This would be a more difficult integral to evaluate because it's got 2 roots in it as opposed to 1, but it's probably on an order of magnitude about the same level of difficulty. Now we want to take a look at the same function and the same solid, but instead work it as a type 1. Let's project into the xy plane. If we project into the xy plane, we're casting our flashlight either down or up the z-axis. So we have to integrate the single integral with respect to z first. In that case, we need to figure out what it's going to look like so we know what the limits of integration are. We're again changing the order of integration. Now we're going to do z first instead of x first. If we're going to do that, we're casting the shadow into the xy plane. So to find what that domain in the xy plane looks like, the projection, go ahead and take z out of it. Now, it's off a little bit because CalcPlot 3D is trying to represent a three-dimensional shape in what is essentially 2 dimensions. So you get some aspects. But basically, you're looking at this semicircle from the side. So what you're really getting, if you're really thinking about it right, is you're really getting, well, a rectangle, right? And it's very hard to get it to kind of show that. But you can see here that it would basically be a rectangle, which is in fact the easiest shape to integrate across. So it may be that the projection into the xy plane is the best one to start with, but it may affect the double integral and make the double integral more difficult. Let's now go ahead and take a look. So we're looking at this. It's basically going to be a rectangle where x is going from 0 to 5 and y is going from 0 to 3. That makes this projection, the double integral, quite simple. And now we have to figure out what the limits of integration of the insidemost single integral would be. To get those, we again want to revert back to our shape, and we want to put the axis we shined the flashlight down vertical, pointing up. In this case, you want to hit the home key, which will put z going up. If we look at this shape, realize that what we have on the top down to the xy plane is the upper half of the semicircular cylinder. And what we have on the lower half is the lower half of the semicircular cylinder. So when we're looking at this, that means that we need to take our equation for the semicircular cylinder, y squared plus z squared equals 9, and solve it for z. And that will give us our limits of integration with respect to z. So in this case, the integral becomes the integral from negative the square root of 9 minus y squared to positive the square root of 9 minus y squared with respect to z. Then on the outside, we're integrating the double integral on a rectangle, which is the simplest surface. The limits of integration for y are 0 to 3, and the limits of integration for x are 0 to 5. So this orientation, this change of variables, has made the single integral a little more complicated and difficult to evaluate, but it's made the double integral part far simpler. So what is the best method for you depends on your own particular skill level and the way your brain works. Go ahead and pause the video now to work this one out and verify that you do get 90 again. Then turn the video back on so we can compare our results. When we integrate the integrand y with respect to z, Y is a constant, so we get YZ evaluated between negative root 9 minus y squared to positive root 9 minus y squared. This will enable us to then write that we have 2y times the root of 9 minus y squared as our new integrand, because a double negative makes it, of course, an addition. Then we were going to integrate this with respect to y, for which we need a u substitution. We let y be 9 minus y squared, and then the derivative du becomes negative 2 dy. And 2y dy, which we have, becomes negative du. We substitute the limits of integration such that when y is 0, 9 minus 0 squared is 9. And when y is 3, 9 minus 3 squared gives us 0. This does reverse the limits of integration from y equals 0 to 3 to u equal 9 to 0, but we also got the negative introduced as part of replacing dy. In this case, we can use the negative to switch the limits of integration, and this gives us the positive integral of u to the 1/2 to u from 0 to 9. When we evaluate this, we get 2/3 u to the 3/2 between 0 and 9, which results in 18. This then gives us the outer integral with respect to x from x equals 0 to 5 of 18 dx, which gives us 18x, or again, 90. The question is, can we still work this as a type 1, where we're projecting into the xy plane, but reverse the order of integration on the last two? And the answer is yes, we can. We can switch the order from dy dx to dx dy. In this case, because we're integrating on a rectangle, all the limits of integration on the double integral are constants. And that means we can simply switch them without any loss of generality. And this is what the integral would look like, still as a type 1, so integrating with respect to z first, with the same limits of integration, then with respect to x from 0 to 5, which would simply treat that 2y, the square root of 9 minus y squared, all as a constant, and then we would have an x tagging along, and then that would give us a 5, so then we would have 10y, the square root of 9 minus y squared, for the integrand of the outer one with respect to y from 0 to 3. Let's take one more look at the same one. We've done now 4 different orders of integration, and we have one left to do, which is treating it as a type 3. In a type 3, we want to project into the xz plane, which means our flashlight is shining along the y-axis. Again, x out towards us, z up, y to the right and to the left. So the flashlight is on the y-axis, casting the shadow into the xz plane. So what would it look like if we do that? In that case, return to your shape, and to get it projected into the xz plane, take y out of the equation. So to take y out, we press Alt and then Y. And this time we get a very, very nice rectangle, which we can see coming out here. So we've got x going from 0 to 5, and z looks like it's going from some value down here up, so from -3 to 3. So it looks relatively straightforward for the outside double integral limits of integration. So the double integral will be straightforward again. What about the initial single integral on the inside? To determine that, we need to return to an image where y is pointing straight up instead. Let's go ahead and take a look at what that one would look like. And I'm going to rotate it a little bit so you can see it. So the y-axis is pointing straight up. Z-axis is pointing off to the side. Now, when we're looking at our region, notice that the top is, of course, that cylinder, but it's the upper half of the cylinder. And the base in the y-axis is y equals 0. It's in the xz plane. So it looks like it's going to go from y equals 0 up to the surface of the cylinder. Now, to get the surface of the cylinder, we take our equation, y squared plus z squared equals 9, and solve for y. That will give us plus or minus the square root of 9 minus z squared. But again, we only want the upper half, and so we take the positive radical. Let's take a look now at these images that you can see here. Here's the rectangle, and this is our shape. Now we've turned it so that the y-axis is pointing up, and you can see that the bottom is, of course, y equals 0, and the top is given by that semicircular shape. This gives us limits of integration on the inside with respect to y of 0 to the root of 9 minus z squared. Then the outer double integral is over a rectangle, so those limits of integration are constants, x from 0 to 5, and z from -3 to 3. Go ahead and pause the video here to work this one out, and this time try as well to write the triple integral, the iterated integral, for switching from the order dy dx dz to dy dz dx. Then turn the video back on, and we'll compare our results. When we integrate y with respect to y, we get 1/2 y squared evaluated between y equals 0 and the semicircular top square root of 9 minus z squared. This gives us 1/2 times the quantity 9 minus z squared as the new integrand for the double integral on the outside. When we evaluate this next with respect to x, none of the integrand has x in it, so we simply consider it a constant, and then we get 1/2 x times quantity 9 minus z squared, evaluated between x equals 0 and x equals 5. This is going to introduce a 5 into the integrand, so we get 5/2 times the quantity 9 minus z squared for the integrand for the outermost integral with respect to z, from z equal -3 to z equal 3. Again, we can keep the 5/2 on the outside as a constant, and when we integrate 9 minus z squared, we get 9z minus z cubed divided by 3. Evaluating between -3 and 3, again, gives us the value of 90 overall, which is the same value we've gotten every time before. You can also keep this as a type 3, projecting into the xz plane, but reversing the order of integration of the outer two. In this case, because it's a rectangle, it doesn't matter which order you do the outer two in. And this integral, this triple iterated integral in blue here, would represent the order dy dz dx. And again, notice that because the outer double integral is on a rectangle, all the limits of integration are constants, so we simply switch the order. Let's take a look at an example now where that's not the case, where switching is going to cause the limits of integration to change because one of these we're not projecting onto a rectangular region, we're projecting into a different kind of shape. Let's take a look at example 10. In example 10, we again are going to use the function f of x, y, and z equal to y, but this time our solid is going to be the region, the solid shape trapped by the planes, x equals 0, which of course gives us, well, x equals 0 would be the YZ plane, and y equal 18 is going to be something, of course, where y is 18, so it's parallel to the XZ plane. And then the slanted plane, z equal y minus 6x, and the plane z equals 0. When z equals 0, of course, we have the XY plane. So we've got our four boundaries, and to be quite honest, it's quite difficult at first to really tell what you're looking at there. So let's come over to the region and sort of see what it looks like when we trap it. Now, when you first graph it, you'll notice that CalcPlot 3D has a little bit of trouble with the graphing. You can see that the edges are not smooth. So to fix that, you want to click on 3D mode until you get to BSP triangulated. And that's usually the second or third. There's two forms, triangulated and not triangulated. You can use either one of those. and it will produce a good picture. I generally have better results with BSP triangulated. And notice how it smoothed out the intersections where those two surfaces are coming together. So now that we have this created, let's go ahead and shrink it down a little bit and try rotating it so we can figure out where our solid is. Now, the pink is forming one of our planes, so it's got to be on the inside of that, but the other plane is the XY plane, so it's got to be above the XY plane, and then it's going to be to the left of the pink plane, y equal 18, but it's got to be below that slanted plane and also in front of the plane where x equals 0. So in front of the blue plane, if you will. So when we're looking at it, we've got this region in here that is going to be in octant 1 below the slanted plane. And in order to find out what the region is going to be trapped by, we need to see what the projection of it looks like as we project down into the XY plane. When we project down into the XY plane, you can see what we're getting right here in the 2D trace plane. So in the 2D trace plane, you can see that there is a line here. It looks like it goes through the origin, and it goes up to y equal 18, where that pink plane is cutting things off. So this is what it looks like in the plane when that slanted plane slices through octant 1. So in order to be able to tell and plot this as a region, we'll use the slanted plane for the surface, the 3D surface, the top, and then we'll use z equals 0 as the bottom. And then for our 2D image, we're going to use y equal 18 as the top and the slanted line to be the bottom. Now again, how do we get the equation of the line? Well, this is where the slanted plane cuts through the XY plane. So we're going to take the equation of our slanted plane, z equals y minus 6x, and we're going to set z to be 0 because that's what it is in the XY plane. And that gives us the equation y equals 6x, which does seem to match what we had in CalcPlot 3D. So we want to graph the region that is below 18 and above y equals 6x, under the slanted plane surface and above the XY plane. And note that x has to start at 0 and y has to stop at 18. And z, of course, has to be greater than 0. Let's take a look now at what it looks like when we plot this as a region. When you plot it as a region, remember that you have to give a 3D top, which is our slanted plane. The 3D bottom is the XY plane, z equals 0. The two-dimensional top is referring to what the projection of it looks like in the XY plane. That gives us 18 as that horizontal line on top. And it gives us the slanted line y equals 6x on the bottom. And then x goes from 0 to whatever value is right here at the intersection of y equals 6x and y equal 18, which of course would be x equal 3. So we plot x from 0 to 3. Let me go ahead and turn off the other shape so that you can see the solid that is forming our domain for this function of 3 independent variables. And now you can see the solid here. It's similar to the one we did in example 3 in the first part of this video series on 5.4, in that each side of it looks sort of like a triangle, but it's a 3-dimensional shape. Now let's go ahead and talk about how to integrate the function f of x, y, z equal to y across that restricted domain. Now that we have the restricted domain and we have an example of what it looks like, since we projected into the XY plane to get our region plotted, we can go ahead and integrate with respect to z first. In the XY plane, the flashlight is shining down or up on the z-axis, so it becomes the single integral. If we orient it this way, we can tell that the top, of course, is the slanted plane, z equals y minus 6x. And the bottom is the equation of the xy plane, z equals 0. That gives us the limits of integration on the innermost. And then we want to look at the projection into the xy plane, which of course is this right triangle you see in the 2D trace plane. When we look at this one, notice that y is varying between the line on the bottom and the horizontal line y equal 18 on top. That means that y is a function of x. So y will vary from 6x on the bottom to 18 on the top. And x then is varying from 0 to 3. Go ahead and pause the video to work out the triple iterated integral, then turn it back on and we'll take a look at another change in the order of integration. Let's go ahead and look at the integration of this integral. We projected into the xy plane, so we're shining the flashlight down the z-axis. So the inside single integral is with respect to z first. The integrand function is y. This becomes yz evaluated between z equals 0 and the plane z equal y minus 6x. This gives us a new integrand of y squared minus 6xy. When we take that and we integrate with respect to y, we get y cubed over 3 minus 3xy squared. Now this needs to be evaluated between the lower function and the upper function on the projection into the xy plane. The lower function is y equals 6x and the upper function is 18. One thing that may help you to figure this out is to draw a vertical rectangle here. And you can see that what it's touching on the bottom is the lower function y equals 6x, and what it's touching on the top is y equal 18. Then we integrate and substitute our values, and we have quite a bit of simplification that we have to do. When we're done, we have a new integrand of 36x cubed minus 972x plus 1,944. We integrate that with respect to x and evaluate between 0 and 3. When integrating, we end up with 9x to the fourth minus 486x squared plus 1,944x. When we substitute in our values from 0 to 3, the lower limit of integration doesn't add much. It just adds in zeros. But the upper limit of integration gives us a final value for the triple integral of 2,187. Now, as we work through the way to change the limits of integration, we're not going to go ahead and recalculate all of these, but I do want you to at least know what the result is on at least one of them. Now, if we wanted to still treat it as a type 1, but reverse the order of integration on the outer two, then what we're talking about doing is coming up here to our projection into the xy plane, and instead of writing y as a function of x, writing x as a function of y. Now, since our equation is y equals 6x, then we can actually think of this as x equals y divided by 6. Another way that you can do this is simply to flip the image so that the x-axis, positive x-axis, points up and the positive y-axis points to the right. It can be a little tricky to get it to work that way, but let me see if I can do it for you. So you can see that I've now flipped the graph so that it's shaped differently. I have the positive x-axis up and the positive y-axis to the right. When I'm looking at this, I'm considering x as a function of y. The lower function then, of course, is just going to be, well, the 0. And the upper function is going to be y divided by 6. So the lower one here is x equals 0, and the upper is the original equation solved for x in terms of y. This is going to change our limits of integration. Let's move on down here so that we can take a look at what that might look like. When we get that done, that means the inner limits of integration that vary inside single integral doesn't change, since we're still treating it as a type 1 projection into the xy plane. That still goes from z equals 0 to z equal y minus 6x, that slanted plane. Then we go with respect to x next, x equals 0 to x equal y divided by 6. And finally, we look at the values that y varies between, which is now 0 to 18, as you can see on the image here on the left. Notice that when our middle integral is a function of the outside integral, and we change the order of integration, that we change the limits of integration. If we were integrating on a rectangle, that's not necessary because they're all constants. But when the inner integral depends on the outer integral, and you change the order of integration, you change the limits of integration. Let's now move on to a different view. Now we want to switch and shine the flashlight down the x-axis. This means we're projecting into the yz plane. So we're going to have dx as the innermost differential. This will require us to write the equation for the slanted plane in terms of x. We have z equals y minus 6x, which gives us the equation x equals y minus z divided by 6. We know that the minimum value for x is x equals 0 because one of the planes that divided our region was x equals 0. So in this case, we want to take a look at what it looks like when we have the x-axis pointing up. This will enable us to find the limits of integration on the innermost integral, the single integral. So in this case, we're going from the plane x equals 0 up to our slanted surface. So when we're looking at this, we're going to have that for the limits of integration on the innermost. Now we need to decide what we want to integrate with respect to next. The next thing we might consider is taking a look at what it looks like when projected into the YZ plane. When x is gone from the equation, we have the projection into the YZ plane, which looks like this. In this case, we've got the YZ plane, and I've actually done it with y as a function of z rather than z as a function of y. Let's take a look at it out here on CalcPlot 3D so we can look at it without the x. Now this is z as a function of y. Oh, it won't let me. Hang on just a second. Let me get that back out of there. Right click and move it down. There we go. Now you can see that z is written as a function of y. The one that is vertical is the independent variable, and it depends on the horizontal one. If we want our middle differential to be y, then we have to change this so that y is pointing up and z is pointing to the right. In order to do that, you would rotate it 90 degrees to the left and flip it horizontally. And if you do that, you would end up pretty much with the image that you see here. So I've rotated it 90 degrees to the left and then flipped it horizontally. Then you have the y-axis pointing up, you have the z-axis pointing to the right. This represents y as a function of z so that we can have y as the middle differential. Now, when we look at this, again, it helps to draw this rectangle, which will help us decide what's the curve on the bottom and what's the curve on the top. The curve on the bottom is a line that we can see here, which appears to go through the origin. And the top is that horizontal line y equal 18 again. But in this case, we've got to figure out what the equation of this line is. It doesn't look like the line that we had previously. In this case, if we take x out of the equation of the slanted line or the slanted plane, we just get y equals z. So this equation is simply the identity function y equals z. Now, the last thing we have to determine are the limits of integration on the outside. Let's go ahead and write down what we've figured out so far. So what we got from the beginning part is we're going to go with respect to x first, which means that x is going from 0 up to y minus z divided by 6. So our innermost integral goes from x equal 0 to x equals y minus z divided by 6. Our integrand is y dx. And then on the outside, we have this double integral over the projection into our YZ plane. This is what we got from the first part. Let's now add to it what we found from the inner differential by looking at the projection with the y pointing directly up. So again, our innermost integral is going to be x equals 0 to x equals, I've forgotten what it was again. Let me scroll up. Y minus z divided by 6. Y minus z divided by 6. The integrand is y. We go with respect to x first. And then we're going to go with respect to y. So the next set of integrals is going to go from y equal, well, on the bottom, we have that slanted line y equals z. So this goes from y equals z to y equal 18. And this is going to be with respect to y. And then finally, we need to evaluate with respect to z. So our outside-most integral is going to be with respect to z. Looking at this right here, what are the values of z that we get used? Well, the maximum value of y is 18, and this point right here is on both curves. So if we have y equals z and y equal 18, then our maximum value for z also has to be 18. So it's going from z equals 0 over to z equals 18. Right? So you get this integral that you see here. And you can see it in finer print right there. Now, what if we want to reverse the last two? If we want to reverse the last two, then we need to reorient the projection so that z is the middle differential pointing straight up, and y, the last one, is pointing out to the right. So this is more easily found on CalcPlot 3D. So when we're looking at this region again, the innermost integral does not change because we're still treating this as a type 2. And then we're going to be integrating with respect to z next. So when we're looking at this green region here, on the bottom, since z is now vertical, the bottom, of course, is z equals 0, and the top is that line where z equals y. And so we have the integral from z equals 0 to z equal y. And then we can evaluate what y varies between, which is 0 to 18. Now let's go ahead and finally rewrite it by putting the differential dy on the innermost integral. So we go back to our top surface, which is the slanted plane z equal y minus 6x, and solve it for y, which gives us y equals z plus 6x. Now we know that we also have the plane y equals 18. So y is going to vary between z plus 6x and 18. Let's take a look at the region with the y-axis pointing up. When you have the y-axis pointing up, you can see that you've sort of, well, put your solid on the tip here. And when the y-axis is pointing up, the slanted plane is the bottom surface, and the top surface is that plane y equal to 18. This would give us the innermost limits of integration of y equal the slanted surface, which I believe we found to be z plus 6x. And the upper surface for y would be 18. The integrand is y, and we're going with respect to y first. Then on the outside, we have a double integral over the projection into the xz plane. And this would be the area differential. So let's suppose we want to do the differential dz for the middle one. If we want to do the differential dz, remember that we're projecting into the xz plane, so we need to return to our picture over here, and we need to get y out of it. So we hold down Alt and hit X, and now you can see that I have z represented as a function of x, and this is the projection into the xz plane. You can tell that on the bottom, z is starting at 0, and on the top, we have a line which is connecting our value of z equal 18 at the top with some value down here at the bottom when z equals 0. And how are we going to find that value? Well, again, we're on that line, which is the projection of the plane into the xz plane. So in the xz plane, y is 0. So if y is 0, that's going to give us z equals negative 6x. So this line has to be z equal negative 6x. So we're integrating from z equals 0 to z equal negative 6x. That will give us the limits of integration of the middle one. And then what is x varying between? Well, we were given that x equals 0 is a bounding plane, so we can't go below that. And then it's going to come up here, and if z equals negative 6x, this value has to be 3. And that's what would cause it to 0 out. Let's now come over here, or not negative 6x, 18 minus 6x. So I forgot about the y. I need to shift the whole thing up by 18. So my limits of integration on the inner are z equals 0 to 18 minus 6x, and x goes from 0 to 3. And then you can evaluate this. If you want to switch the last two, then you need to switch your image so that x points up and z points to the right. And this is going to allow you to rewrite this equation, z equals 18 minus 6x, in terms of x equal to 18 minus z divided by 6. And then x will vary from 0 up to 18 minus z divided by 6. And then on the outside, we would have limits of integration for z, which would go from 0 to 18. And this is what the image would look like if it were rearranged, the projection, into the xz plane, but with x as the dependent variable and z as the independent. And you can see that we've got the equation 18 minus z divided by 6 here as this slanted line, and the bottom is x equals 0. And the value of z varies from 0 to 18. And again, you can go ahead and evaluate all of them. There are two versions that don't have fractions, so choose whichever of those you think might be easier to evaluate. I chose to take a look at this particular one and wrote out all the details for you. And notice that we do come up with exactly the same value that we did earlier on. Move on to the video now over section 5.5.